In the last lesson, we very briefly talked about convolutional networks and discussed the limitations of feed-forward neural networks in classifying images. Convolutional networks are much more efficient, effective, and accurate. Convolutional networks are a specialized form of artificial neural networks. We've dealt with the most basic form of an artificial network, where we have a feed-forward network that contains some number of hidden layers and an output layer. And based on how many hidden layers we have, determines the depth and complexity of the neural network. And then, through some learning rates, learns to adjust the weights in all connections of the artificial neurons to eventually come up with a model with a small training error. We saw how regular neural networks through a feed-forward operation will pass an input through a series of hidden layers, where they are processed on every single node of the layer, until it finally reaches the output layer, where a prediction is then made based on the outputted probabilities. Convolutional networks are very different, as they are comprised of three types of layers: the convolutional layers, the pooling layers, and the fully connected layers. The general similarities being, we have an input layer that takes in our data, and an output layer that makes a prediction. This is the simple neural network architecture that we'll use to classify images in the MNIST dataset. Just like before, the input layer is where we pass in the pixel values of the image, where in this case is still 784, and we're still going to have 10 output nodes from 0 to 9, each one corresponding to a class for which the number being passed in belongs to, where we're still making use of the softmax function to make a final prediction. In between the input and output layers, we have a series of convolution and pooling operations, followed by the fully connected layers. For the rest of the video, we'll focus on the convolutional layer of the neural network. From the name itself, it is apparent that the network employs some kind of operation called convolution. In fact, the main building block of the convolutional network is the convolutional layer. Their primary goal is to extract and learn specific image features that can be used to help classify the image. Suppose we had the following image, where each pixel is denoted by some pixel intensity from 0 to 255. This entire image is the input, and each pixel corresponds to an input node. All of these inputs, all of these pixels, inside of the convolutional layer, are going to be processed by a convolutional filter, which is also known as the kernel, or kernel matrix. These kernels, these filters, are generally small in spatial dimensionality. Since we're dealing with a 3x3 kernel, what we're doing is applying a 3x3 convolution on our image. Kernel convolution, though it may sound overly complex, is actually really simple. We can perform the convolutional operation by sliding the kernel at every location of the image. The amount by which we're shifting the kernel at every operation is known as the stride, a term that you'll hear quite often going forward. In this case, the stride is 1, which makes it such that the filter moves 1 pixel at a time. The bigger the stride, the smaller the corresponding feature map. What I just said might not mean much to you at the moment, but it will make much more sense momentarily. Let's look at a smaller image for simplicity. The area where the operation takes place, the highlighted area, is known as the receptive field, whose dimensions correspond to the size of the kernel that you're using. In this case, we're performing the operation on a 3x3 receptive field. And inside the receptive field, what we do is multiply every cell in the receptive field with the corresponding cell in the kernel. I'll take you through it just once. 100 times 0, 100 times -1, 255 times 0, 100 times -1, 100 times 5, 255 times -1, 100 times 0, 100 times -1, 255 times 0, which results in the following numbers. We then take the sum of all the numbers resulting in a value of -55. Then, taking the average by dividing by the number of pixels in the receptive field, and the result obtained is shown in the following feature map. We then slide the kernel by a step size of 1, shifting our receptive field 1 unit to the right, and perform the same operation. And once again, taking their sum, dividing by the number of pixels in the receptive field, resulting in another value that's displayed. We keep doing that until we've convolved the kernel over the entire image. Which eventually results in the following feature map. Notice how the general feature of the image is preserved, such that there is an edge between small pixel intensity values and the larger pixel intensity. Why is this called a feature map? That's an odd name. Well, remember, the primary purpose of the convolutional layer is to extract and learn specific image features, features that we can use to help classify the image. And the feature map contains a specific feature of interest, which was extracted from the original image, in this case, the edge. That being said, the kernel itself is the feature detector. Convolving the kernel over the image is what we use to extract some feature from the original image onto a feature map. Accordingly, every kernel is trained to have a distinct set of weights, which is what distinguishes one kernel from the other. Here are some very common examples. The values of the weights in the kernel are learned by the convolutional neural network during the training process through a gradient descent algorithm, which acts to minimize the error function by changing the kernel values to the ones that are best able to detect features in the image. We'll talk more about that later on, but it's the same concept as before, where we used gradient descent to update weights in the direction that minimizes the error the most. In our case, it's going to be in the direction that best classifies the handwritten image. But that being said, convolutional neural networks possess an ability known as translational invariance. The idea is that if a kernel is able to detect a feature in one part of the image, since we're convolving it throughout the entire image, it is likely that it can detect the same feature somewhere else. In this case, this kernel, which was made to detect diagonal lines in the image, when convolved throughout the entire image, will identify both diagonal lines on the corresponding feature map. We'll see an example of that in the next lesson. But essentially, by sharing weights, you enable the network to learn a single filter for a feature in the image no matter where it appears in the image. Different filters are able to detect different features from an image. The more filters we have, the more features we can extract from the original image, and thus improving the neural network's ability to recognize patterns in unseen images. So in the case of this example, what we did is we performed 3 convolutions on the same input. In each convolution, we used a different kernel, each kernel corresponding to its own feature map. Combining all of these feature maps gives us the final output of the convolutional layer, a depth of 3 feature maps, where each feature map detected a distinct image feature, which is then further processed by the neural network. For this image, for instance, at first we used 15 different kernels. We therefore end up with 15 different feature maps. We stack them up along the depth dimension to form the full output volume of the first convolutional layer. The deeper the resulting feature map, the more features we extracted, and thus improving the network's ability to classify the image. What we've dealt with so far is known as two-dimensional convolution, and it's what we're going to use when applying convolutions on the images obtained from MNIST. The reason being, which is quite obvious considering we've already talked about it, is that the input of grayscale images are two-dimensional in the sense that they are only represented by a single channel of pixel intensities, whereas RGB color images would be composed of 3 channels and are thus three-dimensional. They not only have a width and a height, but also a depth, where depth corresponds to the number of color channels. Accordingly, when dealing with a 3D image, the kernel will have to be three-dimensional as well. Your kernel, instead of it being just a 3x3 kernel, it would be a 3x3x3. The depth of the kernel must match the depth of the image. In the case of our code for this section, we'll be dealing with a two-dimensional 28x28 grayscale image, and thus we will work with only two-dimensional kernels. Not necessarily 3x3, could be 5x5, but our depth will always be 1. Before we conclude this lesson, just so that I can reinforce the concept of feature detection, here's a kernel with its own distinct set of weights. When convolving this kernel over the image of a truck, we can use it to detect edges in the image. We can use different kernels with different weights to detect curves in the image, ridges, regions of interest, so on and so forth, by simply changing the values of our filter, since recall an image is just a 2D matrix of pixel intensity values, and the filters themselves are also just numeric matrices. We'll look at more intuitive examples of feature detection in the next lesson, but to conclude this lesson, I just want to emphasize that we previously mentioned image processing with regular neural networks would result in models that are way too big, way too complex. This actually boils down to how each node in the subsequent layer of a regular neural network is fully connected to the input value. Going back to our previous example, where we had an RGB image 72 by 72 corresponding to roughly 5,000 pixels, and again, since we're dealing with a 3-channel colored image, where each pixel corresponds to 3 pixel intensities, resulting in roughly 15,000 input nodes, and as such, each node in the hidden layer would contain 15,000 weights. Roughly 15,000. If we were to add even more nodes in the hidden layer, then there just wouldn't be sufficient computational power to run the neural network, since each node in that hidden layer is parameterized by roughly 15,000 weights. The more we add, the more weights, the more parameters that need to be updated during the training process. Whereas with convolutional neural networks, every node in the hidden layer is only connected to a small region of the input volume. To put this into perspective, if we had the same exact image with a kernel and a corresponding 3x3 receptive field, this makes for 9 weights, and to account for the depth of the volume, since this would be a 3-channel colored image, the 9x3 would correspond to each kernel only having a total of 27 weights each. I hope I was able to put things into perspective as to how much more efficient convolutional networks are. Alright, and now after convolving the 3-dimensional kernel onto the image, which in turn would result in a 3-dimensional feature map, we then apply the ReLU activation function. The reason being, any kind of neural network must contain non-linearity, since most of the real-world data that the neural network is required to learn is non-linear. Yet the convolutional operation itself, when we convolve the kernel throughout the image, what we're doing is performing a matrix multiplication and addition between the kernel and the image. This is a linear operation, resulting in a linear feature map, to which the ReLU function is used to introduce nonlinearity. Here's an example of a feature map, to which we apply the ReLU activation function, and what it does is it converts all the negative pixel values in the feature map to zeros. Note that we can also make use of the sigmoid function that we've seen all throughout this course, or even the tanh function, which we haven't really covered, but it's also an activation function. Both tanh and sigmoid are also non-linear, except ReLU empirically will generally perform better in most situations. As opposed to the sigmoid function, the ReLU function is more biologically inspired. It is more biologically inspired in the sense that neural activity does not follow the positive and negative symmetric curves of a sigmoid function. Rather, the lowest level of activity of a neuron is 0, and its action potential frequency can be ramped up from there. Now, just a side note as to why we're using the ReLU activation function is that the sigmoid function, or even the tanh function, they're predisposed to a common artificial neural network problem called the vanishing gradient problem. At a very basic level, this problem refers to a decreased feed-forward gradient within the deep neural network. As discussed earlier, deep neural networks rely on gradient descent and backpropagation techniques to adjust their weight parameters. This is essentially how they learn. However, if the gradient in the network gets too small, or effectively vanishes, then the network is unable to make use of gradient descent in an efficient way, and learning slows down significantly. If the gradient is small, then the network can only adjust weight parameters by a very small amount with each update, which means the network learns very slowly. This problem affects the sigmoid function, because the sigmoid function has a relatively low gradient, as it levels out at extreme values of infinity and negative infinity. It is the most steep in the middle. However, even at this point, the sigmoid function has a maximum gradient value of 0.25. This becomes an issue as within a neural network, the gradient value is fed forward through the network and multiplied with additional gradient values. If the sigmoid activation function is used, then all these gradient values are limited between the range of 0 and 0.25. As we know, multiplying many decimals together creates a smaller and smaller number. Therefore, as the network feeds forward, the gradient in the network seems to vanish to a very low number. This issue can be fixed by using the rectified linear unit, the ReLU activation function. The plot of this function can be seen here. Viewing the plot, you can see that the ReLU function returns a value of 0 if the input is negative. However, if the input is positive, then the output that's returned is just the same value. The key thing to notice though is that the gradient value of the ReLU function is either 0 or it's 1. In the case of a gradient of 1, we know that the vanishing gradient problem cannot occur, as multiplying by 1 does not cause the gradient value to decrease. Regardless, if you think about it, this is kind of analogous to the structure of a regular neural network, where if you imagine a single perceptron, using the weights parameterizing the network, we determine the score, but then we make use of an activation function to determine the outputs. Well, almost the same thing here. We use the weights from our kernels to produce feature maps, but the feature maps, then they must go through an activation function to produce a final output value. So we've introduced the convolutional layer, and we've seen what it does. Before moving on to talking about the pooling layer, or the fully connected layer, let's reapproach kernel convolution with a very simple and intuitive example. We'll do that in the next lesson.